Hey guys, STAT1800, Chapter 9, Fundamentals of Hypothesis Testing. What we're going to look at is we're going to look at um, just the basics of hypothesis testing. Hypothesis testing plays an important role in the rest of the class. Just to give you just a quick preview, this week we're going to look at, or at least in this set of videos, we're going to look at one sample hypothesis testing. Next, we get into two sample hypothesis testing. Then we get into ANOVA, analysis of variance, which is also hypothesis testing, followed by linear regression, multiple regression, which is also hypothesis testing. And then we get into chi-square test of independence and chi-square goodness of fit, which, as you guessed it, is also hypothesis testing. So, I think it's pretty clear that that we need to get a very solid foundation of hypothesis testing because the rest of the class relies on it. So, guys, again, take good notes. I'm going to throw so much stuff at you over the next the remainder of the class that when it comes time to study for your final exam, which is comprehensive. So you're going to have all the stuff we had before the midterm, plus you're going to have all the stuff that remains. So, guys, please keep that notebook. If not, you're just going to drive yourself insane when it comes, like the week or a couple of days before you're studying for the final exam. Trying to put everything together. Okay, guys, let me tell you what's going on. I'm going to put this video up, but I'm also going to follow it up with a video which you either can or cannot watch. This is more the going with the textbook. The next video I put up is one that I put up for my STAT1850 class, which is kind of a lay approach at hypothesis testing. So watch this one. If after watching this video you feel pretty good about the fundamentals of hypothesis testing, then you may be inclined to skip the next video. But if you watch this video and you're still, okay, some of that stuff makes sense, but I'd like another approach, another perspective, then watch the following video. So, guys, the objectives, what we hope to accomplish is we want to get just a basic foundation of hypothesis testing. The two types of problems we look at are hypothesis testing for a population mean and, or I should say, a population hypothesis test for a population proportion. We're going to get into assumptions and consequences and stuff, but not in this video. So first of all, what's a hypothesis? I think of a hypothesis as a claim that's based on an educated guess. Now, in hypothesis testing, it's a claim about a population parameter. So what if I just wanted to take an educated guess on the weight, average weight of all refrigerators? Well, I'd glance over at my refrigerator and I would think, wow, that thing looks pretty heavy. I've got some experience, in moving and different things, helping friends move, on lifting these things. I'm going to say average weight's about 250. That's just an educated guess from things I have in my past about the weight of this particular appliance. Now, if somebody says, hey, Doug, there's this object out in Tulsa, Oklahoma, what's its weight? Well, I don't have any idea. I don't have any educated guess because I don't have any background because I don't have enough information. So, guys, it's not a random guess. It's an educated guess. So one example, let's say that there's a particular neighborhood and one of the people in the neighborhood makes the claim that the average monthly cell phone bill in that neighborhood is $42. Well, hypothesis testing is the tool for you, the tool that you could use to test that claim or that educated guess. Another example, one that corresponds and aligns with population proportion, maybe a university administrator or administrator of a large university claims that the percentage of students at that university who own cell phones is 82%. Well, since we're talking about a percentage, that's a proportion problem. And the notation that this textbook author or the authors use is pi equal 0.82. Now you'll see me use p a lot, but for consistency, pi is actually a pretty good choice for the population proportion. Guys, there's two components of the hypotheses. First one is the null hypothesis. It's denoted H sub O. And the other one is the alternative hypothesis. And depending on the textbook, just to add to the confusion of this, some textbooks use H sub 1 as the alternative hypothesis, and some use H sub A. So guys, I'm old school. I use H sub A. It's H sub 1 business, just kind of hit statistics education. So in future videos I put up, please keep in mind that the alternative hypothesis, which I'll talk about here in just a second, the notation could be H sub 1 or H sub A. Well, anyway, guys, the null hypothesis states the claim that is to be tested. So here's an example. Let's say a manufacturing engineer has concerns about a particular manufacturing machine that creates or makes bolts that are supposed to be 30 millimeters. And they look on the specifications of the machine, and it says that the mean diameter will be 30 millimeters. But there's some suspicion about whether the machine is working correctly. So the claim or the assertion to be tested would be stated as a population parameter. So you're going to make a statement about all bolts manufactured by this particular machine. Now, since you're making a statement about all or the population parameter, your null hypothesis must be stated in terms of mu. And you can see on the right-hand side down by the picture of the bolt that the H sub O x bar equal 30 is not acceptable because it's got the big red line through it. You don't make a claim about a sample value. You make a claim about a population value. So this claim in the null and the claim in the alternative hypothesis, which I'll talk about in just a second, always deal with mu or p or pi, depending on the notation we use, notation for population and not sample. Guys, the null hypothesis, again, H sub O begins kind of with the assumption that the null is true. Kind of like what we hope when there's a jury trial, right? I don't know if that's always true, but you hope that the person is assumed innocent until they are proven guilty. So we kind of assume that the null hypothesis is true until there's evidence that emerges to indicate otherwise. So guys, the null hypothesis deals with the status quo or the historical value. It always contains either equal to, not equal to, or equal to, less than or equal to, or greater than or equal to. Now, I'm not a big fan of this null hypothesis being anything other than equal to, but this book, and rightfully so, there's nothing, it's logically sound. There's nothing wrong with it. If it was, I wouldn't use it. With having greater than or equal to or less than or equal to in the null hypothesis. But I'm not a fan of it, but I'll adapt and make it happen. I always have just equal to in the null hypothesis, but again, I'll get over it. I'll work it out. So anyway, this null hypothesis can be either rejected or not rejected. Now, the alternative hypothesis, again, it's either H sub 1 as used in this textbook, and sometimes it's H sub A, represents the opposite of the null. Now, guys, I like to think of the H sub O as kind of the lazy statement. The H sub O is, everything's fine, that machine's not, there's nothing wrong with it, we don't need to test it. And the alternative hypothesis is the aggressive, always trying to find fault, always challenging the status quo. So here, the alternative hypothesis would be that the manufacturing process is not working. It's not creating bolts of an average of 30 millimeter diameter. So it's, again, challenging the status quo. Guys, it never, ever, ever contains equal to, not equal to, I'm sorry, it never contains equal to, less than or equal to, or greater than or equal to sign. Uh, it always includes not equal to, greater than, or less than. So it may be proven, but typically the alternative hypothesis is what the researcher kind of sets out to prove. Okay? And guys, there doesn't have to be, in this example about the mean diameter of the manufacturing bolt, it doesn't mean that the engineer is setting out to prove that the manufacturer, that the machine isn't working correctly. It's just there's a concern, and it's the alternative hypothesis represents the concern. Like if let's say that we're going to get into two sample problems, and here's an example of it. Let's say that I was concerned that a score on a calculus final, that males and females were scoring differently. So that would be my alternative hypothesis, that the mean score on the exam is different for males than it is for females. It's not really something I would set out to want to prove, because I certainly don't want gender bias contained in my calculus classes. But if I want to examine it, that's what I would be examining, is the alternative hypothesis. Because if there's something like that going on, we would want to make the obvious changes in the way that we present our curriculum. So guys, the hypothesis testing process, it always, I think in learning something new, it's kind of nice to embed it in some sort of illustration. So let's say that, a city manager, for some reason, it looks around and says, you know what, I think the population mean age in our city is 50. And someone else says, you know what, I agree with you, I think it's 52. Well, guys, there's no need for a test of hypothesis. But if someone says, you know what, I think you're wrong, I don't think the mean is 50. I don't know whether it's really higher or lower. I just think it's something different than 50. Then you would set your H sub O, colon, mu equal 50, which is the claim from the city manager or the mayor, however, whatever I said. And then H sub 1 would be what you think you're going to find, that the mean's not equal to 50. Again, H sub 1, and again, that could be H sub A. You'll see that a lot in my videos, is ultimately the motivation for the test. Again, city manager says, hey, it means 50. You're like, I don't care. Okay, it's 50. You don't need a test of hypothesis. But if you want to challenge the statement, the challenge is embedded in the alternative hypothesis. No, I don't think the mean is 50. So let's test it. So again, that's embedded in H sub 1 or H sub A in some of my videos. Process would start like this. You would collect a random sample from the population. So I'd close my eyes, randomly select 20, 30, 100 people. I'd ask their ages. I would hope that they told me the truth and didn't lie about their age. I don't think I've ever heard my mom not lie about her age. She's been 29 for I don't know how many years. But I would take their age, I would add them all up, and I would divide by however many people I have in my sample, and I would get a sample mean. The next process would be to compare the mean with the claim of 50. Now, if I get a mean of 20, 20 is a long way from 50. That would lead me to suspect the claim of 50 and probably even reject the claim and say the alternative is true. I don't think the mean is 50. But what another example, what if I got an x bar equal 49? Well, 49 is really close to 50, right? So I don't think there's any evidence there because it's so close to the claim. And I know all about sampling variability. I know that if I went in, 1 second and pulled out 50 people from the city and got their age, and 1 second later I got another 50 people and got their age, I know those ages would vary. So there's nothing really holy about this particular sample mean that I got. It's one of infinitely many that I could create, but it's the one I use, right? So if I've got a mean of 20, that's a long way from 50. That would lead me to suspect the claim of 50. But if I got a mean of 49 from my sample, which is really close to the claim of 50, then I would say, you know what, that's awful close. I don't think that's far enough away from 50 to reject or suspect the claim of 50. So, third bullet, if the null hypothesis is true, the probability of getting such a different sample mean, and this is focusing on the x bar equal 20, would be very small, so you would reject the null. And repeating that third bullet, if the null hypothesis were true and our x bar was 49, then the probability of getting that sample mean would be very large, so we would fail to reject the null. So in other words, getting a sample mean of 20 is so unlikely, you conclude that the population mean most likely isn't 50. And that's one of the things you've got to kind of tattoo to the brain, is that you've got to use softer language. We don't say, well, the null hypothesis is true, or the alternative hypothesis is true, or, you know, we don't use those words. We just say most likely isn't 50, because we'll get into some errors here in just a second. So guys, the sampling distribution of x bar is tied closely into the hypothesis testing process. Remember a week or two or so ago we talked about sampling distributions of x bar, normally distributed, mean, mu sub x bar, sampling the standard error, sigma divided by the square root of n. You know, I taught you that ad nauseum. I think it's some of the harder stuff in the class. So anyway, guys, if we think about the sampling distribution of x bar, and we pull one of those out at random, and in this illustration it's 20, if it's unlikely, based on probability, that you get this sample mean, assuming that the population mean of the distribution in this case is 50, then you reject the null hypothesis that mu is equal to 50. Now again, if I got an x bar of 49, that would be really close to the mu of 50, and that would lead me to not reject the null. All right? It would lead me to fail to reject the null. Now, how do we make these decisions? Well, these decisions, there's going to be two ways I'm going to teach you. The way I'm looking at it right now is called the test statistic and critical value approach. There's going to be another approach I'm going to teach you, which is much easier, called easy for you to say, a test statistic and a p-value approach. Okay, so again, two ways we can do these problems. They end up giving us the same decision: a test statistic and critical value versus a test statistic and a p-value. So guys, first bullet, if the sample mean is close to the stated population mean, then we don't reject the null hypothesis. And officially we call that failing to reject the null. If the sample mean is a long way from the stated population mean, then we reject the H sub O. We reject the null hypothesis. Well, guys, that kind of leads you to a kind of a clear question. Well, what do you mean by close and far? Those are kind of subjective determinations. So statistically, you know how rigid the things we do in statistics is. How far is too far? You know, kind of where is the line in the sand that determines when a sample value is too far away to have any faith in the value that is stated in the null hypothesis? Well, guys, we do that with what's called a critical value. So the critical value creates this line in the sand. It's kind of like, you know, when I'm go on vacation and maybe I'm at the condo or the resort or wherever, and the place I want to go, you know, I'm always thinking, okay, do I want to take like the golf cart or do I want to walk? Well, depending on the day and depending on, you know, what I've been doing, my line in the sand for deciding whether I walk or drive is usually about a mile. That's usually my line in the sand. If it's more than a mile, I'm going to jump on the golf cart and go. If it's less than a mile, I usually walk. So, just maybe a non-statistical example. So guys, back to the sampling distribution. See those big black stars on the horizontal axis on the sampling distribution? Those things are called our critical value. And I'm going to teach you how to find those things. So smack dab in the center of our sampling distribution, that line, that vertical line, that's where our value for H sub O is. So we assume we're drawing a sample from that distribution. So if we get something to the right of the right black star, see where the blue area is up to the right, then that's called our area of rejection. Look at the left black star. Anything to the left of that is another blue area. That's also a region of rejection. Anything between those two big black stars is close enough to the claim in the null hypothesis to where we end up saying, okay, it's not exactly the claim, but it's close enough. So these critical values define what's close enough and what's not close enough. In other words, what's too far away from the mean of the sampling distribution or the claim in the null hypothesis. All right, risk. And I don't want to go into this a lot because I'm going to put up one video, probably about a 20-minute video, where we're going to dive into these type 1, type 2 errors a lot more. But just to get the ball rolling and to get this definition down, guys, a type 1 error is rejecting a true null. And that's not good. If the null is true, then we want to keep it around. If the average age in this particular city we talked about earlier is 50, then we don't want to reject that if it's true. So that's an error. The notation that we use for the probability of a type 1 error is called alpha. So it's that little Greek letter. It kind of looks like a fish. That's lowercase alpha in the Greek alphabet. So that's the probability of a type 1 error. It's also called the level of significance of the test. Guys, alpha is usually set at 0.05, but I've seen other cases where alpha is set at 0.01, 0.001, and 0.10. I've even seen a case where alpha was set at 0.25. And guys, this is a value that's typically set in advance by whoever is conducting the test of hypothesis. Type 2 error is failing to reject a false null. So if the mean isn't 50, the mean age of the people in this particular city isn't 50, then you'd want to reject it. Well, if you fail to reject a false statement, then you've created an error. And in statistics and hypothesis testing, this is called a type 2 error. Guys, the probability of a type 2 error is given as beta. So our level of significance and the rejection region depends on our level of significance. So guys, when you get ready to set to conduct a test of hypothesis, the very first thing you do is you establish your null and your alternative hypotheses. The second thing you do is you set your level of significance, because your level of significance defines your critical values, and your critical values define your rejection region. And ultimately, guys, what we're doing in hypothesis testing is we're leading to a decision. And in this illustration right here, where there's a hypothesized value for a population mean of 30, if we're to the right of the yellow star, that's to the right of 30, or if we get a mean that is to the left of the yellow star that is to the left of 30, we fall in the rejection region. If we fall between the two values, between the two yellow tails, we're in what's called the fail to reject region. So what happens when we reject H sub O? Well, a reject H sub O means there's more support for the statement in the alternative hypothesis. If we get something between the two yellow values, the two yellow stars, then there's more support for the null hypothesis that the mean is 30. So guys, this is a two-tailed test, and again, go ahead and just tattoo this one to the brain. If you have an alternative hypothesis that has not equal to, you have a two-tailed test. If you have an alternative hypothesis that is greater than or less than, then you have a one-tailed test, and you embed all of your rejection region only in one tail. Now that's to be learned later. If that doesn't make much sense to you, it just means that you're normal. That's something that I've got to teach you at in a later video. So guys, speaking of later videos, our next video, well, the next video I'm going to put up, actually, this is actually incorrect. The next video I'm going to put up is kind of a lay approach at hypothesis testing. Again, it's one that I put up for my STAT1800. You can watch it or not. It's totally up to you. If you just watch this video and you're still a little shaky, things are still a little unsure, then I'll highly recommend that you watch that video, because I break it down I think, into simpler terms. If you've read this and maybe you've got a little bit of background in hypothesis testing, then I think it's reasonable for you to skip the next video that you'll find on Blackboard and go ahead and get into hypothesis testing for the mean. Well, guys, that's all I got. Hope y'all doing well, and let's learn some more about hypothesis testing. Take care.